Dear students, we are going to talk about continuity of convex slash concave functions, and this is an important topic. Convex functions have this beautiful property that if you take a convex function defined over open convex set to R, then that function is always continuous. This is amazing. Whenever you have an open set as a domain of a convex function, then it is always continuous. Hence, the same story would go for a concave function because one is just the negative of the other. So if f is continuous, minus f is continuous. Okay. Or if minus f is continuous, f is continuous. Now, if you talk about a convex function defined on a closed set, this might not always be the story. Because consider the function f defined from on the interval 0 closed to plus infinity, means the line r plus, that is all non-negative numbers, real numbers. So you're mapping a function, you have a function f from that set of non-negative real numbers to r, and you define it as f of x square when x is strictly greater than 0, and f0 you define it as 1, it is above 0. So there's a discontinuity there. But if you draw the epigraph, you just draw the graph of x square and just draw the epigraph, you will see that the epigraph would not be a closed set, but the epigraph would be a convex set. Because remember, 0 is not a point on the graph, 0, 0 is not a point on the graph. 0, 1 is a point on the graph. So there is no chance of convexity of this set getting broken. So you see also when you draw, you will see a very different looking convex set, not the nice ones that we keep on drawing. So here there is a discontinuity at 0, though the function obviously is convex because the epigraph is convex. There are a lot of books. For example, if you look for economics, if you look into the book by uh, you know, any book, I would say, like by R.K. Sundaram, a first course in optimization, uh, then that book would actually give you a very nice proof about the convex continuity of a concave function. Now, what we are going to do is we are going to take a slightly different view. We are going to show that convex functions defined over an open convex set already lies within a class of continuous functions called the local ellipsis functions, and that is what we are going to now define. So given a function from an open convex set, in this particular set, for a general definition, you just need an open set, not an open convex set. We just do. So if you define a function f from u to r where u is open, you can take it convex, no problem. We say that f is Lipschitz at x naught, which x naught point in u, if there exists a delta greater than 0 and an L greater than equal to 0, such that for any yz in an open ball centered at x naught and of radius delta, the modulus or the absolute value of fi minus fz is always less than equal to L times norm of y minus z. That's the distance between y and z. So this constant L is called the Lipschitz constant of f at x naught. Now it naturally depends on the chosen point x naught. If L does not depend on the chosen point x naught, and for every x naught this L remains the same, we say f is globally Lipschitz over the whole of U. So if this definition is satisfied at x naught, we sometimes say f is locally Lipschitz around U. Means if you take some point within any other point within this neighborhood, you can again show that the same L will work for all, and L will work for any other point if you want to choose, and take a small neighborhood which is contained within this ball. Then at each and every point you can show that L that the function f is Lipschitz with the Lipschitz rank L. So means within this ball, the function is actually Lipschitz with the Lipschitz rank L. So that's what we are going to now show through these following two results. And these results, what we describe here, first appeared in 2006 in a book called Convex Functions and Their Application, written by Niculescu and Persson. One of them is from Romania and one of them is from Sweden, and both are experts in the analytic aspects of convex functions. So they give the two theorem, we take the proof style also. We had the, when we take the proof style, maybe our writing is different, but the idea comes from their book. What they show first is that if you define a convex function over an open convex set, so you take open convex subset of Rn and take f to ur is a convex function, u to r is a convex function, then f is locally bounded. That is, if you give me any x naught in u, I can find a set V subset of Rn such that x naught is within V and f is bounded on V. Bounded means the function value has an upper bound and a lower bound on V. Let us now consider V to be a cube in Rn. We are trying to give a proof of this fact. A cube means if you have a cube in Rn, it is actually a polytope. If you look at a cube in R3, a cube in R2 is a square. Cube in R3 has 8 points, 8 vertices. It is a convex hull of 8 points. So because it has 8 vertices, you can very well understand what I mean by the vertices of a cube. That is why this is very intuitive, this result. Similarly, a square has 4 vertices, a cube has 8 vertices, and so on. A hypercube has 16 vertices, and so on. It just gets multiplied by 2. So when you are in n dimension, it must have 2 to the power n vertices. Hypercube in I should have written hypercube, but okay, doesn't matter. Hypercube in n dimensions. So actually V essentially is a convex hull of 2 to the power n points. So any x in V can be expressed as a convex hull of these 2 to the n points. So I am not writing the details of, I should write that any point x element of V is expressed as this, and I am not writing the lambda is in details because you know that what the lambda is are. So then using the convexity of f again, you get this one. Using the convexity of f again, you get f of x is less than is equal to f of this, and by convexity you get that f of x is less than equal to lambda 1 f1 plus dot 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 lambda 2 to the power n v to the f of v to the power n. Now when you line up these values of the functions at the 2 to the n vertices, we have 2 to the power n numbers, and you just take the maximum value among them. So let that be m. Obviously there's one of the vertices where the maximum is achieved, at least one of the vertex. Then from this expression, I know that fx is less than equal to m because it will be lambda 1 n plus dot dot lambda 2 n m. And take the m outside to the right of the bracket, then the sum of all the lambdas would be equal to 1 because you are essentially, that's a stuff that comes out of the convex combination. Now V being a cube is symmetric. So if I know there is a point x, and I can always find a y because of the symmetry of the cube such that x not equal to x plus y by 2. Of course, you can ask me to prove this, but it comes from symmetry. Certain things are very clear from symmetry in which you don't need to go and additionally prove. So there would be a point y in V for which x naught can be written like this. So what did I prove here by proving fx less than equal to m? I have proved here that giving me any x, I shall prove that fx is bounded above on u, on V. Now here I am trying to now bound it below. So I use this symmetry idea and write x naught is x plus y by 2, where x is already this x which I had taken, this arbitrary point, and I find another point y which is symmetrically is from the same distance from x naught as x is from x naught. You can always do that because it's a cube, there's a symmetry. There's a very nice rectangular symmetry, and so that's a very, sorry, cubical symmetry, and that symmetry is very nice because you can have equal distances on both sides. So whatever distance x naught is there from x, the same distance x naught has from y. So x naught is equal to x plus y by 2. So x naught being the center. Now, so f of x naught is less than equal to half of x plus half of y by convexity of f. From here we will have 2fx greater than equal to 2fx naught minus fy. So y is a point. So any point y, but we know that fy is less than equal to m, that we have already proved, because f of x is less than equal to m for any m, any x actually, x was arbitrary. So from here I can write fx is greater than equal to 2fx naught from this equation minus fy, but fy is less than equal to m, so fy is greater than equal to minus m. So what I get, fx is greater than equal to 2fx naught minus m. X naught is a fixed stuff, so 2fx naught is a fixed value, and minus m is a number, so there is a fixed number. So f is actually bounded below also, which means f is both bounded below and above on v, and hence f is locally bounded. Now you can say, okay, instead of a v, why didn't you do it on a ball? Proving this on a ball would also not be very problematic. You just have to take x naught inside the ball. The problem with the ball is that you cannot do this kind of thing. Of course, you can take any fx and you can write it as a, because once you take any x, you cannot express this as a convex hull of certain thing, a convex combination of certain things. So doing something on the ball is slightly difficult. Just you can say, okay, why don't you take a ball and proved it is bounded above on the ball? So what we did is that we did it on a cube. Now if I can put a ball of radius delta such that the open ball is completely contained in this cube with the center as x naught, then this function is also bounded above and below on the ball, which is very natural, right? Because whatever is the lower bound over the set v, it will be lesser than the lower bound that will be achieved on a ball inside it, and the upper bound of the ball would be lesser than the upper bound achieved by the function over the set v. So even if you put a small ball inside, you can always get that the function is bounded above on the ball. See, the idea is very simple, that we have to use this convexity idea somehow. So we created this nice cubical stuff. So you have a polytope. See, here you are again seeing the use of a polytope. Now you use the polytope idea and show that it's bounded above and below in a polytope. So I can only obviously say that it is bounded below on a ball of radius some delta dash, which is completely contained inside, because the center point, because it's inside the cube, it is an interior point. Because it's the center. So you take the center x naught, you can always find the ball which is completely contained within V. By the fact that x naught is the center, it's the interior point. And by definition of interior point, you can find such a ball. So once you have that ball, you know that it is also bounded above and below on that ball too. So you can always consider a ball that given an x naught, I can always find a ball on which the function is bounded. But this is a very, very nice trick. So that is why you take the cube, because you can use that convex combination idea and actually apply the definition of a convex function. Now we come to this fact of convexity and Lipschitzianness. So what we will show that f is Lipschitz on U. Once f is Lipschitz on U, you can prove that f is continuous on U, because every local Lipschitz function is continuous. So every convex function u on Rn is locally Lipschitz on that open convex set, and doesn't matter if you have a concave function, the conclusions would remain same. So you start again with a point x naught element of u, And you know that it is locally bounded at x naught, so we can always find the delta greater than 0 and an open ball around x naught on which it is bounded. So now in that open ball of radius delta, consider a smaller concentric ball of radius delta by 2 and choose x and y from that smaller ball. Okay, so I choose x and y from that smaller ball. And now I'll show that for any x and y in that smaller ball, the Lipschitz condition would be satisfied with some L, and I'll have to figure out that L. So define a Z in this fashion, where delta comes from this delta and y and x are given within this. So if you take a norm of z minus x naught, if you take z minus x naught here, you subtract x naught from both sides, you will have y minus x naught here. So norm of z minus x naught is norm of y minus x naught plus delta by 2 norm y minus x, norm y minus x. So this is a real number, it will go out of the norm, real non-negative number. So norm y minus x and norm minus x will cancel and you will have delta by 2. But y belongs to a ball of radius centered at x naught and of radius delta by 2. So y minus x naught is less than equal to delta by 2, showing that z is in this open ball, because this will be strictly less than delta by 2. So this will be strictly less than delta. Okay, showing that z actually belongs to the bigger ball. Okay, of course z could be actually inside the smaller this ball also, but definitely it is within this ball. That is the meaning. Now a simple calculation from here will show that I can express y as a convex combination of x and z. Observe this coefficient and observe this coefficient, because delta is obviously less than the numerator, 2 norm y minus x is less than the numerator, these are less than equal to 1 quantity is greater than equal to 0. But when the sum of this quantity, this coefficient and this coefficient, the sum is 1, which you can easily see. So it's a convex combination, and by convexity we will have this that f of y is less than equal to this coefficient into f of x plus this coefficient into f of z. Now you subtract fx from both sides. Subtract fx from both sides, right? Once you subtract fx from both sides, a simple calculation would show that this is true. Now please understand that delta plus 2 norm y minus x is bigger than equal to delta. So 1 by delta plus 2 norm y minus x is less than equal to 1 by delta. So applying this fact, we will come to a conclusion like this, and let me see how. I know that f is bounded above on bx not delta, that is open ball of radius delta, I know that. So I may not call bounded above, I can just say it is bounded, just not bounded above, bounded, which means that there exists a greater than equal to 0, m greater than equal to 0, such that mod of fp is less than equal to m. I should here not call bounded above, it's called bounded. So that is mod of fp is less than equal to m for all p within this. Now if you write fz minus fx, right, so fz minus fx is less than equal to mod of fz minus fx, which is less than equal to fz mod fz plus mod fx. But z and x both are lying within this ball. X is actually inside a much smaller ball inside. So for both of them, mod of fz is also less than m and mod of fx is also less than m. So mod of fz plus mod of fx is less than 2m. So the whole thing is less than 2m. So you will put this thing back here. So you will put 2m here, and 1 by this is replaced by delta. That will, because 1 by delta is greater than 1 by this. So you will have here this is less than equal to m here. So m 2m here. So 2 into 2m, which is 4m, divided now by delta into norm y minus x, that is this norm y minus x which is left. So we'll have this. Now if I switch the roles of x and y and make the same argument, I'll get the same result. Fx minus fy is less than equal to L. I just switch the roles of x and y. Instead of here y plus this, I just put x here and x minus y here. That's it. So then I will get a condition like this. Now if I take a minus in this condition, it will become fy minus fx is greater than equal to minus L times y minus x, which is this. And this by definition means that the absolute value is less than equal to L times norm y minus x, showing that f is locally Lipschitz, hence f is continuous. I leave it to you to show that if a local Lipschitz function is continuous, because given any epsilon greater than equal to 0, if I say delta, if I put delta is equal to epsilon by L, then for all y minus x less than equal to delta, for them, because delta is epsilon by L, mod fy minus fx would be less than epsilon. So continuity is guaranteed. So continuity of Lipschitz function is guaranteed, and every convex function on open convex set is locally Lipschitz. So which means that f is also continuous. So essentially what I have proved that it is locally Lipschitz at x naught, any point on the open convex set. So it is locally Lipschitz at all points, and hence it is continuous at all the points on U. So the concave function is also continuous at all the points on U. So with this, let me conclude today's very important discussion. Thank you very much.